Well, that was interesting. That was a nice slow motion translation into going live there. My computer is doing this wonderful thing called thermal throttling, and it is being super slow for some reason. So I'm hoping that we're going to be able to overcome that. And until we do, I want to do some introductions and talk about what we're going to do today. So with me, I have a very special guest, Joe. Joe, do you want to introduce yourself? Say hi, or how to do.
Sounds good. Thanks. Hi, everyone. I'm Joe Camerly. I'm a product security engineer here at Salesforce.
And so, out of curiosity, what does a product security engineer do day to day?
A lot of what I do day to day is essentially as an internal security consultant to our engineering team. So I work with our developers who are building the Salesforce products, make sure that they're building security into the products, designing them securely, and that we don't let any security bugs slip through.
That sounds uh, stressful. I'm gonna go with stressful.
It can be, but it's a lot of fun too. I come from a development background. Most of my career was as a developer, so it's really nice to work with teams that are working with code. And I have a long history of doing community outreach and teaching, so the the ability to do some more in-depth security training for our engineering teams is really a nice part of the job as well.
Cool. So, over the past couple of, well, I guess it's months now, no longer weeks, but a couple of months, Joe and I have been working on refactoring and building out some features into a project we did on codeLive about a year ago, where I did a session on how we can keep some secrets secret in our Salesforce org. And the example here isn't to use it for things like API keys or connected usernames and passwords for things like connecting to a service. We're gonna use named credentials for that. But whenever we have a secret that we need to keep that is not sort of the name credential side of things, we need a better way to do it. And so the solution that we proposed, that I put together a year ago, was to take and separate the secret and the key itself. So instead of having everything in one place, what we do is we store the secret key that decrypts and encrypts it in a custom setting, and we store the actual secret in custom metadata. And the trick, the secret sauce here is that you can deploy custom metadata records, and you can store custom metadata records in your version control system. But as long as they're in there and they're encrypted, that's okay, right? Is that a good summation? Okay may not be the technical term.
No, it makes a lot of sense, and that is one thing you definitely want to keep those clear text sensitive values out of source control. But a lot of times you want to have the convenience of managing that data within a source control environment, and so having them encrypted in many use cases is a reasonable trade-off of functionality versus security. Again, as long as you're very careful to keep that key material away from the actual encrypted secrets.
So, okay, Joe, let's just back up and take a step. Let's take a step back and back up. Yeah, okay. I'm going full steam ahead today. Can you explain what it means to have a secret and an encryption key, and what those pieces are and how they fit together?
Absolutely. So let's start with a secret or sensitive value, something that you want to keep protected. It could be an API key. It could be something that you're doing as a shared secret for um, JWT signing or encryption, anything that's particularly sensitive. A lot of what we're going to cover with this material is using symmetric cryptography to protect that data, and that is, you can think of it similar to a lock and a key. If you have a lock, and anyone that has a key that's keyed to that lock can open and close it. So with symmetric encryption, you're using the same key to both encrypt the data and decrypt the data. So protection of that key is critical, because if someone knows that key, they can decrypt any data that you've encrypted with it and therefore read it, and your confidentiality is compromised. They can also use that encryption key to re-encrypt data that someone may think has come from you or come from an authorized source because it was encrypted with that single symmetric encryption key. We won't go too deep on asymmetric encryption, but that's another fun set of topics that I haven't gotten to build into this code base yet.
I was going to say symmetric. What does that word mean?
Yeah, so symmetric is where the same key will both encrypt and decrypt the data. You have one key, and it's
gotcha.
essential that you keep it private.
Gotcha. So to do this, a long time ago, a year ago, I put together the secrets class, and the secrets class was sort of all cobbled together, done with the back of a napkin design. And Joe found it and decided he wanted to make it better, faster, stronger / more secure. And so he and I have been working on this for a couple months. You featured it in your talk at TDX a couple weeks ago, and what we have now is this overarching secrets class, but it has a couple of things that go along with it. So we have secrets, we have secrets custom metadata query service. We've got a secrets custom storage base, custom meta storage base. We've got secrets data, and we've got the secrets key service. And so we've got a whole lot of stuff here. I'm just going to open them all up, and then we'll be able to sort of walk through them, and we can talk about how we architected this. I'm thinking about busting this out into its own repo, so if you ever want to be able to have a drop-in solution, you don't have to put all of Apex recipes in your org. You'll be able to install a package that has this there. But like any other security-sensitive code, just because you found something that you think works doesn't mean you don't have to read through it and understand it and make sure that it is secure to the best of your knowledge and have your company sign off on that. So we've got all of these classes here, and the first thing I want to do is sort of go over our custom keys, not that one, custom key storage service and the secret storage service. These are interfaces, and we're going to go through this code base and sort of talk through why we did things here. And then we're going to start off with these two interfaces, the secrets key storage service and the secrets storage service. Both of these are interfaces. Joe, talk to me a little bit about why you wanted to bust these out and to have interfaces that we then implement.
A lot of that comes from my background development and architecture of abstracting to interfaces so that you can compose different solutions and use dependency injections so that if you want a different concrete implementation, you can very easily do that, and you're not tied to this real strict hard-coded set of functionality. And as you can see from this repository, like you said, we run with this, and we've started expanding our ecosystem of providers. So refactoring to interfaces really gave us that ability to have that abstraction and inject almost anything we wanted as providers.
So for those of you watching along at home or in your office, however you may be, the key to this is when we refactored it out to have these two interfaces, we grew the ability to have multiple different ways of storing the secrets and multiple different ways of storing the keys. And so this secret key storage service here, we've got a get key and a create key, and those two methods must exist in any concrete implementation of a key storage service. Likewise, for the secret storage service, we've got a store, a retrieve, and a create key, which is sort of a pass-through to the key storage service. And doing this, we've been able to do custom metadata storage of the secrets. We've been able to do AWS Secrets Manager storage of secrets, and we've been able to do HashiCorp's Vault storage secrets. So you'll get to see some of those implementations each of time, but we're able to do this with a common interface, which is super important. It also makes our unit testing a lot easier to do. And let's dive into first the most sort of like on platform way of doing this, which is a secret key service custom settings. You'll notice that it implements that key service storage, And we go through here, and here we've got our get key and we've got our create key, which are the two things required for the storage, the key storage service. And as we look through here, what we're doing, let's see, where should we start? Let's look at get key. So we're going to look at get key, and you pass in a name, and we're going to say, okay, where can we get this key? Do we have it in our memoized keys? Memoized keys is a performance optimization where you're not having to query several times for the keys. So in the same transaction, if you use this service more than once, it's only going to run the query to find all the keys once. And to do that, it's got this query for the key name and put them into the memoized keys, and then you're going to return that memoized keys key name. Somebody's asking on the chat, Varun, will this be available on the YouTube channel later on? Yes, it'll be available on YouTube. Pretty much always with the URL you joined with today. So once we've got our key, we can also talk about creating a key. And to do that, we're going to pass through our key name and our key size into a write key. Now, this is our interface method. This is the one we have to have in order to implement that interface. But we have a custom method here called write key that is going to go ahead and put this data out there. So here, if we look for write key, what we're going to find is that it's going to go ahead and create a secrets __ C. Now this is a custom setting object that we've defined called secrets _ C. And as I think about that, maybe we should refactor that to be secret keys. Yeah.
Yeah, naming things is hard.
Naming things is hard. And then we're going to insert it. No big deal. All right, so we're creating keys, we're saving keys, or we're saving keys, and we're querying for keys. And that is all there is to the key service. Now we use that key to encrypt or decrypt the actual secret. So let me close this key service and we'll close that one. And as we look at the secret storage service, you'll see that we've got store and retrieve, which are, they do exactly what you think they do. And then we've got this create key here. Let's look at what we do for the custom metadata service implementation. And what we do here is we tell you that these are your available encryption algorithms. Now, Joe, are these all the encryption algorithms we have on the platform?
Those are the currently supported symmetric encryption algorithms on the platform. And also the key sizes are part of those algorithms. So
okay.
It's 3 different key sizes of the AES encryption algorithm.
So AES, if I remember correctly, stands for Advanced Encryption System.
Standard.
Advanced Encryption Standard, which, again, naming things is hard. I would have, like, advanced seems to be like something that is going to continue to be rolled over in terms of technology. And so I wonder why we didn't go with like encryption standard 2020. Anyway, but that's neither here nor there. This is bigger than Salesforce.
To NIST.
Yeah, that's up to a national organization group. We also have an enum for HMAC algorithm, and I confess I know how to use an HMAC, but not really what an HMAC is. Do you want to teach us all about what that is?
I'll do my best. HMAC is a hash message authentication code. So it's a way of generating a hash of data that requires a seed value as well. So this is what we're using an HMAC for, is so that we can have some integrity checking on our data. So when we encrypt it, we also want to make sure that we encrypt it and we're using a seed value as well as part of that message authentication code, so that we have integrity checking. For our implementation, we're using the name of the value that we're encrypting. so that it's internally consistent, and we can do things like prevent a copy paste style of attack, where if you just have an unauthenticated blob of data that's is encrypted with this specific key, and it may be something particularly sensitive, if an inside attacker can take that value, copy it into the next row down, and cause it to become decrypted, even though it has a different identifier value, that's going to give a breach of confidentiality. So this is just a way of having that data integrity so that we're sure that the value we are working with is the appropriate value, and that it's not something that someone is trying to circumvent our controls.
Now, is it unfair to call this sort of a checksum of the secret?
It's a validated checksum, so
A
it's a
validated
bit
checksum.
more than a
Okay.
checksum. Just if it was just a hash, like a message authentication code, that'd be a checksum. But because we're also adding an identity seed value, throwing that into the algorithm, it's actually an authenticated value.
Gotcha. Okay. Now, as we go through here, we've got this set up because we refactored back to those two interfaces. When we talk about needing a key service in our concrete implementation of a secret storage service, we can just say we need a secrets key storage service. Any concrete class that implements this can be used as a key service. So when we instantiate this object, we can actually pass this in here and say, okay, go use the custom setting key service, or go use the key service for Vault, etc. Anything that implements that key storage service can be passed in here. And let's see here. We've got a couple other things. We've got a secrets custom metadata storage base, which going back to the old joke, naming things is hard. What this is, the secrets custom metadata storage base is a extraction. Let's just open it up here. It's an extraction that allows us to do dependency injection. So there are things in here that we need to be able to do, like fetch the encryption value and to implement the callback from metadata deploy, because remember, metadata records can't just be inserted, they have to be deployed. So we're doing these things in here, and they're ways for us to make sure that we can dependency inject specifically this fetch encrypted value, because we can dependency inject an instance of this object into our key storage service. When we're doing unit tests, we can override or stub this fetch encrypted value so that it's not actually trying to go and grab the secret value. So that's handy. And as we go through here, if you got questions, comments, snide remarks on this, feel free to jump in there. I'd love to hear it. We've got a constructor that takes a key service, so it's going to set that key service. And we've got a constructor that takes the key service, encryption algorithm, HMAC algorithm, and key size, and sets all of these properties for us. And then finally we get down to the create key, where it's going to give us, it's going to pass through the key service that we've specified with the key name and this encryption key size. That was a mouthful, but basically what we've done here is we've set up our storage service to say that we can create a new key if we need to through the storage service, knowing that it's tied back to an instance of the secrets key service and has the same method signature, even if it doesn't have the same implementation, depending on what the concrete instance of this object is. Somebody's here Max is going, is the goal to retrieve encrypted secrets from a key store like Vault and then decrypt on Salesforce server in Apex as needed? Yes. Or Max,
It depends.
Yeah, so that's one option for you. What this system, because I think now we've gone past one class. It's not really a class anymore. Now it's a system of classes. What this system allows you to do is to mix and match your storage medium for your secrets and your keys. And some of those some of those storage systems are things like AWS Secret Manager or HashiCorp Vault, or we have a custom metadata implementation. And so right now we're looking at the custom metadata implementation, but you could do this also with HashiCorp Vault, etc. The idea here is that you'll be able to go and grab your secret, whether it's from custom metadata or HashiCorp's vault, decrypt it, and then do something with that secret temporarily in your transaction, and then discard it, knowing that that secret is safely stored, encrypted at rest, and you don't have to worry about violating confidentiality. So when we have our secrets stored, we want to be able to retrieve them, and we're going to return the secrets data object. And a secret data object is really quite, like, it's in its own class because it's its own top level object, but it's really just these four properties: a name, a key, an encrypted value, and a clear text value. And we use this as sort of an internal data transfer object. Um, Whenever we retrieve a secret, whether that's from HashiCorp Vault or Secrets Manager or the custom metadata, you're always going to get back an object of the secrets data information. So you'll be able to access that clear text value, so on and so forth. So I'm going to close that one down. That's really easy. But what we do here for this concrete implementation of pulling secrets out of custom metadata, what we do is we go through and we fetch the encrypted value from the storage base, which is that method we just looked at that's actually going to go and do the query. We're going to set the name to what you passed in. So you're going to say, okay, great, give me the secret for foo. And it's going to go grab the encrypted value from the custom metadata for foo, and it's going to validate at secret format. Now, the reason we're validating that secret format is we store that encrypted data in a string field. And Joe, you created this the encrypted format. Do you want to describe the? I'm scrolling down through here to find where we have that verify method.
Sure. Yeah, essentially, we just concatenated a whole bunch of pieces of information together into a single long string. I like storing encrypted values more than just the actual raw encrypted value, because then there's no context with it, and you have to have a lot of external support to figure out, what key was that encrypted with, what authentication algorithm was used. So if we store everything together, an identifier for the key, the encryption key, not the actual key value, we know that this particular blob of data was encrypted with this particular key, and that lets us do versioning, it lets us do key rotation, and it gives us that extra bit of flexibility so that we have a single string representation that we can carry along with us from system to system and maintain that connection to all of the pieces of metadata. Well, I'm sorry, that's a loaded Salesforce term. All of the pieces of information about that encrypted value and how we can decrypt and validate that it's authentic in one easy to carry format.
So the easy to carry format that you defined when you created this part was the encryption key name, tilde, encryption algorithm, tilde, HMAC algorithm, tilde, encrypted value, tilde, HMAC value.
I like using tildes. In general, the actual encrypted value and the HMAC value associated with it are base 64 encoded. Generally, tildes aren't used in identifiers for string names, and that so it's a formatting choice that I made that you can absolutely change for whatever delimiters you like. But in order to stuff it into a single string, having some sort of delimiter is nice, and it means I don't have to go out to a JSON or XML representation, just using the simple string value.
Yeah, I really like this. I was going to ask why tilde. Are tildes used in? Is tilde a valid character in base 64?
No.
That's what I thought. So this is, I mean, these two parts of this string are going to be base 64 encoded values. So using the tilde, you can, even looking at it, you can tell that this is multiple pieces of data, because the tilde is not a valid character for either the encrypted value or the HMAC value. So I really like that. This is specific to this concrete implementation, isn't it? We have different validate secret formats for Vault and for AWS Secret Manager, right?
We have a different representation for Vault because we're actually not storing the secret value in Vault. We're using Vault's transit encryption. So Vault is where our encryption keys are managed, and it's providing encryption as a service for this particular implementation. We could also use Vault as a storage engine, but I chose not to.
Okay.
That's the other reason that there is that base class for custom metadata, because I'm also storing Vault encrypted data as custom metadata in this implementation.
Gotcha. Okay. Yeah, that makes sense. So let's back up here. When we retrieve, we're going to validate the secret format just as sort of a make sure everything is sane. And then we've got this, you'll see that what we're doing is we're going to return the secret parts from the validate. So we're going to bust it out by the tilde into an array of strings and populate these bits here. And you'll see that we've got everything from the key name to the algorithm, HMAC algorithm, payload algorithms, and the payload HMAC. And then we're going to finally turn around and grab the key. So given that key name, we're going to pull it out. And then once we have the key and all of that metadata information, we can call this method throw if secret has been tampered with. I'm a huge fan of the guard principle of development, which says as soon as you can, you should check to see if something is sane. If it passes, basic muster, it's not null, that sort of information. And if not, you should throw some sort of exception. So here we have this throw if secret has been tampered with. And what it's going to do is it's going to come down, and we'll jump down here. It's going to do an encoding bit here to generate a HMAC. And this is where we're doing our validated checksum. So if I understand things right, and again, I know what an HMAC is, I know how to calculate and use them, but I've never actually dove deep into the math and the theory behind them. So Joe, correct me if I'm wrong, we take the information that we have from the metadata we've retrieved along with the key that we've retrieved, and we calculate a new HMAC signature based on what we've retrieved from the database. And then we're basically saying these two things should be identical. Is that right?
Almost, but not quite.
School me.
Essentially, what we're doing is our HMAC is an HMAC of the encrypted data. So when we encrypt the data, we take the clear text value, we run it through the encryption algorithm, we get out a bunch of nearly random values. That's our encrypted value. That's what we put into the HMAC calculation along with our key, the name. That gives us what comes out of that HMAC is essentially the checksum, the keyed checksum.
Mm-hmm.
It's on the encrypted data. We append that in our data format. How we're doing our validation here is what comes into this validation is here's the encrypted value. We're not even decrypting it yet. Here's the encrypted value. Here's the HMAC that came in with that payload. Here's the key that came in with that payload. We then generate a fresh HMAC of that encrypted data using that HMAC key, and then we compare it with the HMAC that came in from the payload. If both of those HMACs match, we know that the data has not been tampered with. That the encrypted data is the same encrypted blob that it was at the time it was encrypted and hashed.
Okay, so I understood all the words you just said, but maybe not in the way you use them, because
sure,
I thought I said what you just said.
Okay. The main, I want to make sure that the values that are being hashed and verified are is the encrypted data.
Okay, gotcha.
So we haven't even decrypted it at this point in time.
So without
We
decrypting it, we're checking to make sure that the encrypted values match,
haven't been tampered with.
haven't been tampered with. And we do that
Right.
with the constant time compare. And this is one of the things I wanted to ask you about, because what do you mean by a constant time comparison algorithm?
Okay. There are ways in which information can be leaked, especially when it comes to decryption. So, since we're working with a lot of string values and developers, we like to optimize things.
No. What?
Yeah, so in general, a loop will or a comparison will exit as soon as a difference is determined.
Mm-hmm.
So if we're starting and we're comparing two strings of data that may start the same, there's a certain amount of time that's spent until we get to that first different character, then the loop exit. Constant time comparison is a de-optimization. So you cannot, an external who can observer who can watch the timing of comparison can actually use timing differences to build up an attack string that they can start with a and see how long it takes that comparison to exit and start to build inferences about the data and eventually build a um, by observing timing differences, build up a valid HMAC value
Wow.
by
That's
repeatedly running it through this. It's a
forgive
really
me, but
fun
that
thing
seems
to
very
do. It's a little
tedious.
bit complicated.
Yeah.
And in the Salesforce world, it's not necessarily as relevant because this is all running on platform and there are larger timing differences based on internet latency and everything. Then you probably won't be able, an attacker won't necessarily be able to observe it, but it's still a good practice to have in place. And it's definitely something that can bite you if you're doing something on metal, on hardware. You can actually, a determined attacker can definitely build up attacks by taking advantage of those times when a developer hasn't used a constant time comparison operator for
That's
validating equality.
I mean, I've never even heard of that, but that's fascinating. It's good to know that it's not as big of an issue on the on platform, but this is good
Right.
that we've baked this in.
Right. And this is, again, why copying and pasting crypto code from the internet without having a good security review and making sure that it fits into your um, threat attack scenarios is not the greatest idea. Always make sure that when you're doing anything with sensitive encryption code, you've got someone who's done this before, who's made the mistakes before.
All right. Wow. Okay. Also, this is the first time I've ever heard anyone refer to de-optimization on purpose. So that's again, this is fascinating to me. I remember when you first put the PR in for this, I read over this and I'm like, why don't we just do first equals second? But now this makes a whole lot more sense. Okay. So let's jump back up to where we were in our retrieve method. We're going to check to see if our secret has been tampered with by calculating and comparing an HMAC to the encrypted value. And then we're going to, if that passes and the constant time comparison passes, then we're going to decrypt with managed IV. And I've always wondered, what does IV stand for here? Because when I hear IV, I think, something you get at the hospital.
It's initialization vector. So this is a for symmetric encryption, especially for AES. It's a block encryption. So what it does is it works in blocks of your data. You pass in, a large value, and the algorithm chunks it into blocks that are roughly equivalent to the key size, and performs a bunch of swaps and calculations on that data to transform it to something that's virtually random. To do that for block 2 through n, it uses feedback of what the previous block's value was to feed into the equations. It's a cipher block chaining, so it's chained together. But for that first block, you need some sort of random value to feed into the encryption, and it should be something that's as random as possible, only used once, never used again. That's an initialization vector. And the Salesforce platform crypto classes give us this encrypt with managed IV, where every time you call it, platform generates a new cryptographically random initialization vector to use in that first block of encryption, and it sticks that IV along with the encrypted text, because that's the standard way of representing it. There is no significant risk that comes from appending that initialization vector to the encrypted value. And it does mitigate things like I've seen in my time a number of cases where people just use a static initialization vector that's all ones, all zeros. And what that means is all of your data comes out encrypted deterministically. If you've encrypted the password value of literal password, and you're using a constant initialization vector, every time you encrypt it, it's going to start the exact same way. And that, again, can give an attacker enough information to break the encryption or just to swap it out.
Fascinating. Again, these are things that I'd never even thought of before. But it does remind me of something I know from like, not the non-platform development, where you refer to it as assault. Is the initialization vector the same idea or similar to assault?
Some cases can refer to it as assault.
Okay.
That's usually more used in the context of hashing than encryption.
Yeah.
But
I can
and
see that.
nonce is also another word that's used frequently.
So what we're doing is we're saying, given the payload algorithm that we've determined up here from our deserialized secret pulled from the metadata, and the key value that we're pulling out of our key service based on its name, and the payload encrypted value, the payload encrypted value, which is our actual encrypted secret, we're going to decrypt those things and return a string.
Yes.
Yeah.
That takes that encrypted set of data, runs it again through the decryption using that same key. So that's because this is symmetric encryption. The same key that's used to encrypt it is used to decrypt it.
Now, at this point, you've got a return object, which is that secret data, and it's got the clear text value specified, and that is in memory, correct?
Yes.
Is that a big hairy deal, or is that just it's in memory, now you can do stuff with it?
It's a risk that you kind of have to accept in order to be able to do anything with the data at all.
Okay.
So yes,
So theoretically,
you've done your best to protect it.
At this point, since it's in memory, you could theoretically do something really stupid like system.debug or the clear text value, right?
Yes.
Okay. And
at that point, the risk is on you as the developer.
Right. Don't do that. You could also, you could leak it in any number of ways, but the idea here is that we're going to protect the storage, the at-rest version of this data, so that it's only exposed in a transaction where it's actually being used, is the idea.
Yes, and having that separation of key values means that if someone looks at your source code on your screen and sees the custom metadata that's serialized on disk, they won't have the key, and it will be essentially useless to them.
Again, and so we're separating two things: the key to unlock our lock, and the lock itself are in two different storage mediums, and sometimes in two different systems if we're using AWS Secrets Manager or HashiCorp Vault's secrets system. This is the basic idea of retrieving the data. Now we've got one for, if we scroll down here, we'll have one where we can encrypt the value with the key, where guess what we're going to do there? We're going to take the key and encrypt the data. So this will give us this, instead of doing decrypt with managed IV, we're going to do a encrypt with managed IV, and we can turn around and use that. If we scroll down here, I'm going to go to the store method, and the store method is going to say, we're gonna do some basic guard checking here again. If we have a no clear text parameter, then this is not a valid key, and there's nothing to store basically. And then once we've passed that, once we have a clear text value of our actual information, then we're going to create that encrypted value, which we just saw, create an HMAC for it, and then we're going to base64 encode that encrypted value and create a secret that is serialized. And then we're going to turn around and we're going to create and dispatch the metadata record creation. And this is in that base class. And what this does is this actually triggers a metadata deployment with your new record. And again, if you've not really delved deep into how metadata, custom metadata works in relation to the platform, in relation to, say, a regular S object or a custom setting, you can't just insert a custom metadata record. You have to actually create it and then do a metadata deployment. And you can trigger that metadata deployment from Apex, but you still have to do it, and it is still asynchronous. So while it may take a small amount of time, you can't be guaranteed that if you just go and create a secret that you can immediately go and decrypt it in the next line of code. So just fair warning. Because this is going to create that metadata record, deploy it, and when it gets done, then it'll be available. So we've got the round trip here of creating and retrieving our secrets, and that is for the custom metadata one. Do you want to walk us through how the Vault one works? Because this one is a little bit different, and one thing I want to particularly call out is, it's not the right one. It's the Vault. Okay. The thing we have here is we have the create key method, and we've got the store method, and we've got our retrieve method. But interestingly enough, they don't necessarily do what you think they would. So, I'm gonna turn this one over to you and let you walk us through it, Joe.
Sure. I will preface this by saying this particular implementation does build on metadata for storage. So we are still doing the storage of encrypted values as custom metadata, and we are retrieving that encrypted data from those custom metadata objects. So the mechanism for storage and retrieval is virtually identical to our full-on platform one. The only difference is we are using off-platform capabilities to do the encryption and decryption. In this case, this is an implementation for HashiCorp Vault, specifically their transit encryption function of their application. HashiCorp Vault is a really interesting combination open source and commercial product. It does secret management. It does secure storage of values, but we're not using that particular feature of Vault for this. We are using Vault as the encryption key store. So it's managing all of the encryption keys. So if we look at this, that's why create key is stubbed out. Because our key service for this implementation is essentially null. That's all been outsourced to Vault, and all key management happens through Vault. The only thing that we have is the identifier for the key name. So we have generated a key 01 name in Vault. Vault's managing that key value. If we want to talk about storage, Kevin, you want to scroll us down here?
Yep.
You'll see that the first thing we do is encrypt the value, and to do that we call encrypt data. Encrypt data is what's making those API calls to Vault. It's just I'm using a named credentials because this is there's a set of credentials that are used to generate access to Vault. This is an API key one, so it's a token authentication. Vault supports a lot of different encryption or authentication methods, and we're essentially hiding that from Apex code, that literal value of that sensitive value by using named credentials. This is an appropriate use of named credentials. We're doing our call out, and again, calling out to our Vault instance and using transit encryption, saying, hey, Vault, here is a bunch of data. Please encrypt it with this key. Vault knows the key value. It performs the encryption. And to us, that is opaque. That's up to the Vault administrator to determine what type of encryption is applied to this clear text data. What comes back from Vault is a delimited blob of data. And again, Vault has its own representation of that data. And what we then return is what Vault has determined that encrypted data is, along with all of their delimiters, and then we're just slapping on a preface of the key name that was used to encrypt that data, because we'll need that when we want to decrypt it. We have to tell Vault, here's a blob of data, and here's the key name that was used to encrypt it.
So in this case, what we're doing is, instead of separating our key and data into custom metadata for the data and the custom settings for the key, what we've done is basically put the key in Vault, and we're storing the secret itself in custom metadata. But because the key is in Vault, and the Vault is the only thing that can do the encryption or decryption, what we're doing is we're taking the encrypted value or the clear text value, depending on which way we're going, passing that across the wire with a secure HTTP call out to the Vault itself, where the Vault will encrypt or decrypt and manage our secrets. Is that a good summation?
Yes.
So
yeah.
You said something earlier at the beginning that I thought was really interesting. You said encryption as a service. And I'm kind of intrigued by all the things you might be able to do with that. But just on a sort of whim here, that encryption as a service is what's taking care of most of this. So what we're doing in our encrypt data and in our decrypt data is we're making an HTTPS call out to our Vault system that we've defined with a named credential. Right?
Correct. Yes.
All right. Now, for those of you who are going at home, what's a named credential? Remember, naming things is hard. A named credential is a combination of an endpoint and some sort of access key. And so there are different ways you can set up a named credential in system. It's a platform feature, but you can go in and create a named credential that uses OAuth to a particular URL, or like the AWS secret. What is that one called? The
AWS signature v4.
You've got OpenID. What is the other one?
JWT and JWT token exchange.
Password is your other option.
And you have username, password. Yep.
So you can, when you create this, you're going to say, okay, it only applies to this particular URL. So this Apex token name credential, whenever you see this call out colon and then a string before the slash, what you're getting here is you're getting a combination of an endpoint. This call out can only ever go to the endpoint specified in that name credential, and it will have the ability to apply your credentials, whatever those are, whether they're they need to go into it as a header or a bearer token. All those things are handled for you by the name credential. So we're making a secure call out, and we're going to encrypt or decrypt encode or decode the base 64 version of the results that come back from these calls, and we're going to get a Vault encrypt object back, and this is what Vault gives us back. This is our data transfer object, and we've got this is the important part here. You got some metadata that comes in, request ID, that sort of information, but we also have this data object, which is going to give us the ciphertext, or the encrypted version, the plain text, or the decrypted version, and this key version. Is the key version something different than the key name in Vault?
Yes, the Vault supports key versioning. So there's keys are named, but then they can also be versioned over time. So that allows you to do key rotation without changing the name of the encryption key. And again, that's something, it's more of an internal implementation. It's here because honestly, this class is here because it made it a lot easier to do JSON deserialization. This is what you get back from Vault is a JSON string, and I don't like doing a lot of manual parsing of JSON. I will say Apex doesn't have the greatest JSON functionality, so I found it easier to create a DTO class and use the parse method.
Yep.
That's really the only reason this class is here, is because I'm too lazy to navigate through JSON elements.
No, that totally makes sense. That's how I do it too. Is to create that data transfer object, and I don't have a problem with creating DTO objects and leaving them in my org, because they make it very clear what's going on and where. So whenever we go through this, we've also got our different validate secret object, and we're gonna store it. We're gonna validate that this one has a size of 2. Again, we're basing it on the tilde, and this is because we're getting back the secret data from Vault, and we just have our key with it. It's just the key name and the Vault, right?
Yes. Yeah, and that's because Vault's representation of what you get back from transit encryption has everything else that Vault needs to know. The only thing we need to know to call Vault is, here's the key name that it was encrypted with, and here's the value.
Yep.
The cipher value.
And we've got the opposite here. So we've got validate secret format. We've also got serialized secret.
Yep.
That is just putting the key name and the encrypted data there. So that's the one for secrets Vault custom metadata, where the pairing is Vault for keys and encryption as a service, and metadata for storing a local copy of that. The downside to this particular thing, because it's secrets as a service, if for some reason your secrets service endpoint goes down, all of this will fail, right?
Yes.
There's not a way to locally decrypt a Vault secured secret from custom metadata. You still have to have access to the Vault server that you've specified. So this is
generally, yes. I mean, Vault encryption is using standard and commonly accepted encryption algorithms. So if you had the key stored in Vault and you extracted it, not necessarily in Apex, depending on what encryption algorithm you chose to use in Vault, but it's theoretically possible if you have that private key value and you know the algorithm that to decrypt those values, even if Vault goes down, by just manually doing the decryption.
So, okay. So we could manually decrypt this, but it would be a pain because we probably wouldn't have the key. I mean, having the key available to us would sort of defeat the purpose, right?
Right. Yeah. But I'm saying, your disaster recovery scenario
I see what you're saying.
Having backups of your Vault and failing that if you had the encryption key that Vault uses and stores deep within itself, you can use an implementation of the standard encryption algorithms that Vault uses and decrypt that if you have the key value.
Okay. So
but all in all, it's probably easier to bring up a new instance of Vault and restore into it.
Right. So we've got one implementation left. We've got 5 minutes. They're going to have to make this sort of the, it's Tuesday, we're in Germany, sort of whirlwind tour. And that is for the AWS Secrets Manager. Now, this is a product I was not familiar with. I'm familiar with Vault. I've used it in my previous life as a DevOps guy. But the Secrets Manager, like I Googled it, and I'm like, oh, okay, it's basically Vault by AWS. what sort of pairing, like in the Vault pairing, we had keys and encryption as a service, and then metadata local storage of the encrypted values. How does this one work? Is this the same sort of encryption as a service like the Vault implementation?
No, this is just an implementation of a key management service.
Okay.
So in this one, I'm using AWS Secrets Manager as the repository. That's what's holding the encryption keys. So this is not a storage implementation. This is just if you don't want to use custom settings as a key provider, and say you have an AWS environment and you wanted to have some sort of interoperability and exchange encrypted data with some other system, and you manage those encryption keys in AWS Secrets Manager, this lets you reach into AWS Secrets Manager, grab that encryption key out, and use it for whatever purposes you need. So this implementation is only for a key provider.
And I guess I would have realized that had I read this part. That it only
I
implements.
just pushed the code this morning, so I can't fault you for that.
So we've got a secret key service for the AWS Secrets Manager. So we could mix and match this with our metadata storage service. So we could do keys in AWS and storage in metadata. Again, this does that effective separation of where the two bits of information are, and without both of them together, you're kind of left not able to do anything. So this does provide that security, just in a different way. And as I look at it, we're doing the get key, and the get key is going to call this query for key. And if I look for the query for key here, we are making this call out to AWS with an HTTP request. So we're going to look at the AWS secret DTO class and see what this gives us. And we'll see that we get some metadata. What is ARN?
That's the application resource name. That's the identifier value. And again, this class is just for Java or for JSON deserialization. Yep. This is representative of the data that Secrets Manager API call gets, and I just use it for parsing.
Okay. So we're going to grab that data from AWS Secrets Manager, and that is going to give us just the key. And so here we're pulling that data, that string value of the key. Okay, so that makes sense. And then we just can use that key to decrypt our secrets.
I like this one because it let me do the AWS credential named credential provider. So this is more of an excuse for me to get to play with named credentials for interacting with AWS.
Great. That's right. That's cool. We've got 2 minutes left. I have a couple questions here in the chat that I want to address. Yes, this is being recorded. It'll be available at this URL that you're viewing it on now. As soon as we finish up here, you'll be able to start it over, as I understand it. There may be a slight delay, a couple minutes, but it should be up there pretty quickly. And if you've got other questions, feel free to raise them on the on the GitHub URL. That is github.com/trailheadapp/apex-recipes. You can raise issues, put in PRs, that sort of thing. And I'm happy to field other questions there. And somebody is asking, can we get the code into Apex recipes? Yes, there's a whole pull request review, peer review thing that's going on. It usually takes a couple weeks once we do the show to actually get that code merged into main. If you want to cheat, you can look in the there is a branch called codeLive/secrets 2, and that you'll be able to see everything that we looked at there. If you just go to GitHub and use the GitHub interface to switch branches, you'll be able to see everything we have here today. But I'm going to work to get this merged into main. I have a feeling that my colleagues may request renaming of a couple of things, but that's the kind of thing that peer reviews are for. So we'll have that there as soon as possible. And again, I'm thinking about breaking this out into its own extracted library, sort of like SuperStub or can the user /safely. So both of those are available out there outside of as packages, so you can just install them in your org and use them. But again, this one's going to have a big caveat about how this is security related code, so you should definitely read through it and understand it and be comfortable with it as a guard against your threat assessments. Yeah, so I'll put that there. And with that said, I have it at exactly 2 o'clock. So thank you much for tuning in. Thank you, Joe, for joining me in this and for going through this as well, and I appreciate it. And then, guys and gals, we are taking a break for a few weeks, about a month. We'll be back in mid-August with codeLive, so there won't be codeLive next Thursday, but again, here in mid-August, we'll start back up again. You can follow me on Twitter at CodeFryer, or follow on this Salesforce Developers channel on YouTube to find out more, or subscribe on YouTube to find out when we next